Okay, so last time we finished talking about the TQV formalization. So today, let's talk about a new topic, which is transformers. Okay, so transformers was released by Google in 2017. So last time we talked about attention model. So basically, a transformer unit is a multi-layer such attention layers stacked up together with other neural network layers. So let's talk a little bit about this transformer architecture first. So first of all, give me a sec. Yeah. So first of all, the attention layer with the transformer model, for example, here is a picture from the original transformer paper when they were using it for machine translation tasks. So remember when we were talking about the machine translation, we have two kinds of stages, right? The encoding stage and the decoding stage. So the transformer model, when you use for machine translation, you also have two stages, the encoder stage and the decoder stage. So in the encoder stage, it's very similar to what we talked about last time, which is you try to encode one token, you add one token into the recurrent network each time. So the input, let's first talk about the input. So the input in a transformer architecture is different from the plain like RNN architecture, where here we talk about this picture, for example, where you input one token each time. So in the RNN architecture, so in the transformer architecture, the input has two parts. First is the token. Second is something which they call positional encoding. Okay, we'll talk about the positional encoding later when we dive into the paper. It's mentioned in the paper. And then the input passes through a multi-head attention, which is similar to what we talked about last time about the attention mechanism being used in this machine translation case, which is this one. You see, so then you apply attention, okay? And the attention is self-attention, which means that here we are not seeing a self-attention, remember? So here we try to build the attention between every encoder state and a decoder state. While in the transformer case, we try to leverage the self-attention, which means that for every encoder state, we try to find its attention with another encoder state. So that's the idea, that's the input part of the transformer. Okay, and then we have some other layers. For example, we have feed forward, which is a regular neural network, or we call it fully connected layer or dense layer. And we have normalization layers. And another thing interesting of the transformer architecture is that we have the residual connections, which here is indicated with this kind of a curved arrow, which means that the raw input here, okay, and the attention result, they're added in this yellow layer, which means you took some of the pre-attention input, added with the attention output altogether. You add them all together. So this kind of connection is called a residual connection. Residual connection generally in machine deep learning means that you add the information from one layer and another layer together, and usually these two layers, they do not have to have a they're not consecutive with each other. So this is one unit. This is an encoder unit of a transformer. Okay. Okay. All right. And then you go to the decoder stage. Okay. So let me place the part. Okay. So the first highlight is that they use self-attention to model the correlation between all words in the input sequence in parallel, unlike the step-by-step recurrent encoding. And then the attention is bidirectional. Okay, so last time we talked about what is a bidirectional attention, which is that you try to have the entire encoding state. We have the entire sequence encoded, okay? And your hidden state is not only one directional, your hidden state is bidirectional, okay? And you build attention on such bidirectional hidden state, okay? All right, sorry about the back and forth here. Okay, And then, so the encoder will encode all the input at once, just like we see in the machine learning case. And the decoder will generate one output each time, okay? So the decoder stage, you can see it's very highly similar. The input of the decoder stage is highly similar to that of the encoder stage, okay? So you have the output, right? Because remember, in machine translation, we will generate one output each time, okay? So every time the previous generated output being fed into the decoder. And again, you have this positional encoding. You add the positional encoding onto the fresh input, and then it became the input of this attention layer. Okay, so you have the attention layer, and you have the residual connection to connect the raw input, the input of the attention layer and the output of the attention layer, and you do a normalization. And then we have a cross attention, which means that this attention is between the input in the encoder state, hidden state, and the decoder hidden state. Okay, so this attention is the cross state attention, while this attention here and this attention here, they are self attentions. All right, so after the cross attention, they go to the feed forward network. Of course, they have we have the residual connections and the normalization on the added result, and you pass it through another linear layer, and you go softmax, where you can predict what's the next word to be generated. We have talked about where you use multiple neurons, where one neuron corresponds to one token multiple times. So I guess I don't have to repeat here again. So this is basically the transformer architecture. And here you probably see this notation NX. This NX means that they will repeat this unit for several times, okay? So basically they have this unit, they will stack up for several times. So I think the experiment, for example, they can stack up this N could be 12 times, okay? All right. Yeah, okay, all right. And when they do the attention, they use the multiplicative attention rather than the additive attention. So which means that we will use this attention model approach, this one, okay? This multiplicative attention rather than this additive attention. All right. So that's pretty much the highlights of this transformer architecture. So let's take a look at the original paper. The original paper. Okay, let me go to the screen sharing. All right, so let's look at the paper. Let me rotate it back. So this paper is called Attention is all you need, okay? That is really great. So let's look at the details. So this is architecture. We just spent time to talk about it. Okay, all right. So each layer here, you can see they call it a sub-layer, okay? They call it a sub-layer. All right, so all right, so see, this is a residual connection, right? So this is X is the input, and this one is a sub-layer. So they want to add the sub-layer is basically a self-attention layer. So you can see here it says a multi-head self-attention. That's what they talk about, okay? And then so this is what the input processed through the multi-head attention, and then they want to add it together, right? And then passes through a normalization. So this is it, okay? All right, and then there is something interesting, which is the embedding dimension. So the embedding dimension means what's the dimension of this output of this sub layer, okay? And you can see and this is the attention approach, right? We talk about it, that we will use, this is the multiplicative attention model we talked about earlier. And also we talk about what is multi-head attention. Basically, you repeat this unit for multiple times, and we want the attention to focus on different aspects of the text, right? So for example, one example, which is may not be the different heads that the model learned, is that each head one head could learn translation about gender, one head could learn about translation related with terms, the other header could be related with, for example, polarity. All right, so this is the multiplicative attention model, and I want to talk a little bit about the positional encoding. Okay, so the positional encoding basically says that I want to know the position of a character, sorry, the position of a token in the input sequence. So the author, they actually take a very smart approach. They use a sign function to represent where you are in terms of the input sequence. Okay, so this positional encoding, did they mention here? No, they did not mention here. So the positional encoding is added, according to the figure, the positional encoding is added onto the input embedding, okay, in a pairwise fashion. We will see a picture later, but you know what, let me show you that picture for now. Well, it's not in this picture. Okay, so it's added onto this. So if you were to use the raw approach to build a BERT model, we'll see, I'll give you a demo in a bit. You will need three things as input. The first input is the word tokenized input. Okay, the tokenized word. You will map those tokenized words into integers, and you do their embeddings. And then you have the positional encoding. So these are the two inputs. And there's one more thing, actually, we'll see in a bit, okay? Because the question is, what if your input is of variable lengths? So how do you handle that? So there's another thing which is called attention mask. We'll talk in a bit, okay? But this is the transformer architecture, okay? So note that the decoder, you will feed back the output one each time, while for the input you have the whole thing as one input. You encode the encoder encodes the input all at once, okay? All at once. So it's not like a recurrent neural network thing. So it's all at once as input. All right, any questions? And if you have questions, please use your microphone, because I don't know, whatever in Zoom, whenever I share the screen, I cannot see the text reply, okay? Okay, so if that is the case, let's go back to the slide. Okay, here is a slide. Okay, so I put several links here. They're really good. They give you a good code implementation of how to build a transformer. Feel free to take a look at it. It's very good. I do want to talk about one of the examples. Allow me to skip away from this. Let me talk about one example. Why couldn't I jump? Okay. Okay, all right. So let's talk, let me share screen. Okay, I'll just share the entire big browser. Okay, so you can see, here's a very good tutorial made by Google about how to use machine translation to do the attention. Okay, so you can see here is a picture. This picture actually probably talks better than this picture is, I say, better than the other picture we see about the architecture. So you can see, so for example, in this example, the goal here is to translate a sentence, I think it's in French, to English, okay? So what happened is the input, okay, the entire input, we will, first of all the tokens, okay, we will find their embeddings, and then we will compute the bidirectional, we will pass bidirectional RNN, and then we'll compute, so the bidirectional output of this RNNs becomes the hidden state, became the hidden state of the encoder stage. So this is the encoder stage, and this is the decoder stage. So in the decoder stage, that each of these steps happen one at a time, unlike in the encoder stage, where the encoding happens all at once. And you can imagine why it all happen at once, because we want to have bidirectional attention. Okay, so therefore you cannot move one at a time. You have to look at the whole thing. So forward round and backward round. So this is encoding. This is the embedding hidden state of the encoder. And decoder will happen one each time. Okay, so you feed one word into the decoder one each time. So this is one time step, one time step, one time step, one time step, and a one time step. Okay, and the blue part, as we scroll down, we'll see this is the attention. Okay, so every row here corresponds to the hidden state of one encoder hidden state. Okay, while each column corresponds to one state of the decoder. Okay, so as we move forward, we will compute the attention. The group attention one each time. And remember, we have self-attention for the encoder and the self-attention for the decoder, while here what processes us is the cross encoder-decoder attention. All right, so you can see here is the encoder, the cross encoder-decoder attention being visualized. Okay, so here's a longer example. I guess that this is the French, this is English, and the English translation says, "Are you still at home?" Okay, so you can see there are some high attentions. So the yellow one, I assume it means high attention. So for example, probably you can see this word at, and this word in French has higher attention, while this word in French and this word in English word you has higher attention. Okay, and very interestingly, you can see this state, which represents the end of the French sentence, and this state represents the end state of the English sentence. They both have higher attention. Okay. Okay, and you can see the higher attention, also a higher attention here. Okay, between the French word casa and the word home. I don't speak French, but I think casa means house in French. Is that the case? Because I know there's a very famous movie called Casablanca. And the Casablanca literally means white house in French. Okay, so you can see this cross encoder-decoder attention really works. So the higher attention is between the French word casa and the French word and the English word home. Okay, but very interesting. You probably say, hey, why does it have a higher attention here? I don't know. Probably, I don't know. I don't know whether French has prepositions, but in English we have this preposition at. Okay, so probably that's why this high attention happens here. Okay, I don't know what does anybody speak French? What does this word mean? Todavia. Does it mean the English word you? I don't know. Let's take a look. Todavia. What can I type? Yeah, I realize my computer has really weird problem with Chrome. I can't type. Gosh, let me go back to Firefox and search it. It means to steal. Okay. All right. Okay. So this is this example, and let's see something. So a natural question you might ask is, since we have a neural network model here, so we know that neural networks, they have to have fixed lengths of inputs, okay, because we have to have fixed number of neurons. Otherwise, we cannot build the transfer matrix from one layer to the other, because if the number of neurons in one layer changes, then this transfer matrix needs to have variable number of rows or number of columns. So that becomes a problem. However, here in the transform architecture, we encode the entire input sequence all at once, okay? And we know that the input sequence could have variable lengths. For example, this French sentence has only 3 tokens, while this one has a lot. So a natural question you might ask is, what do we do then if we have variable sentences? Okay, I made a mistake. This is not French. This is Spanish. Okay. All right. So then how do we do that? So BERT introduced, not BERT, Transformer introduces a mechanism called a mask, attention mask. So as we scroll down this, we will see it's called attention mask. All right, so it's called attention mask. So you can see here is one visualization of that. So attention mask basically says how long my input sequence is. And other than that, stop using the attention mechanism. So which means that when earlier on up above, if you want to compute the self-attention, okay, if you want to compute the self-attention, let's say here we only have 5 tokens, including the special token, the start and end of a sentence, we will only compute the self-attention among the first 5 tokens. The rest of them, we do not count about them. We will mask them out. So, and the attention mask is very simple. It's just a binary matrix. So it has 1 and a 0, which means that later when you update those neural networks, we only update the attention corresponds to the first 5 tokens. And for the rest of them, they are masked out. We do not update them. Okay, so this is how to do a transformer using the mask approach. Okay, let me say a little bit extra. So in terms of the input, the first thing you want to do is you want to encode the tokens. The first thing you want to do is you tokenize. Okay, so and that's obvious why you want to tokenize. We talked about that in word embedding. So here is one example sentence. This is not actually an example sentence. Okay, this is actually a vocabulary. So the first thing you do is before you tokenize, you need to build a vocabulary. The vocabulary basically gives every token a integer representation and an integer number, and with that integer number, we can go to the embedding layer to look up for its embedding. Okay, so here it says, for example, you have multiple sentences. Okay, so each row here in this picture represents 1 sentence, and each token we map them into an integer. Okay, and you can see this is the length of the first sentence. Basically, this mask layer, so the yellow part represents 1, the purple part represents 0. So you can see this is the length of the first sentence. Okay, and you can see the token part only goes to here. Okay, rest of them are all zeros. Okay, and this one is probably a super long sentence. So you can see this is a super long sentence, and these are the token IDs. Okay. All right, let's go back to the slide. Any questions? If no more, I'll just leave those examples here. They're really good. You can take a look at them. All right, I'll leave them here for you to read. All right, so next, let's talk about sentence embedding. So earlier we talked about word embedding, right? We talked about static word embedding, where we talk about that in Mokolov's paper. He used the close test to treat computers to do the word embedding, trying to learn word embedding. Do you still remember how his network architecture looked like? Okay, well, so his architecture is that, let me open the paper. Hold on, change it. Remember his network? His network is like this. So you have one central word as input, okay? And you want to predict the context word. That's his network architecture, okay? So this is we call static embedding. And when we were talking about attention mechanism, we talked about the contextual embedding. Remember? So let's go up to very early. So, all right, remember this example I talked about? Basically, we assume that the meaning of a word is a superposition of its context words, okay? And each context word have different weights on influence or dependency related with a central word. So we have this F to represent that. And later we showed that this F is basically the attention. Okay. So by using this attention mechanism, we can find the contextual embedding of every word. Okay. So therefore, we can also do a special kind of embedding, which we call sentence embedding, like that. So what we do is we treat all words in the sentence as a whole, and then its contextual embedding is the embedding of the sentence. Okay, which means that we get the self-attention of all the tokens across with each other, and we do a weighted sum of the word embeddings. Okay. All right. So give me a sec. So what people usually do is this. They do it like this. Okay. Let me show you. This is what they do. They would. So for example, let's say I have a sentence. So let's say I have a sentence. Okay. The sentence is, how are you doing? Okay. So what we do is we will get the word embedding of each of them. So let's call this embedding 1 for the word how, embedding 2 for the word you, and we have embedding 3 for this one, and I compute the embedding for the word doing. So I have the embedding for all these 4 words. And then what I can do is, for every 2 words, I compute their self-attention, right? For example, what's the attention between the word how and are? What's the attention between the word how and you? What's the attention between how and the doing? And we can do that for are, you, and are doing, and you doing. Okay? Then I can do a weighted sum of such embeddings, and I can do a sentence embedding. So which means I can obtain the embedding of the entire sentence. So then you can see how this can be useful, because if you could get the embedding of the entire sentence, you could get you could represent the meaning of the sentence. Then you can do lots of cool things. So for example, let's say you could check whether one sentence is logically related with another sentence, right? So for example, the first sentence says, I am sick today, while the second sentence says, therefore, I'll teach the class online. Now, if you could represent the embedding of these 2 sentences, then you could do a cosine similarity between these 2 sentences. Then if the cosine similarity is 5, you know that these 2 sentences, they're causal, otherwise they are not causal. So let me show you a work made by Google. Yes, let's see this paper. So for example, if we can embed the sentence, okay, then we can compare the similarity between sentences. You can see here is example. So here's one sentence says, I like my phone. Here's another sentence, your cell phone looks great. And here's a bunch of, here's the same sentences, okay? And we can see something interesting, right? For example, these 2 sentences, the first 2 sentences, they're both talking about the phone. So therefore, their semantic contextual embedding is pretty high. While if you look at these 2 sentences, they're both about the weather. So their semantic similarity is also high. And look at these 2 sentences. Very interesting. They do not have the single token that's the same, right? How old are you and what is your age? There's no single token in them that are the same. However, their semantic similarity is being trained to be actually pretty high, right? Because they're pretty much, they mean the same thing, right? How old are you and what is age? They mean the same thing. Okay, all right. So you can see the attention mechanism can really give us good semantic representation of the entire sentence, and it literally makes sense, right? And these 2 sentences, you can see their similarity to other sentences about weather or phone are pretty low. Okay. Now let me ask you this: why does the diagonal part has the darkest color?
It's itself?
Yeah, exactly.
It's the same, yeah.
Yeah, it's a similarity bit of the sentence and itself, right? So obviously that would be 1, okay? So this is a work made by Google. It's called Universal Sentence Encoder. You can take a look how they did it. I want to show you their model, actually. They have a picture, I think. somewhere. They removed the picture. I hit it. They revised the paper and now the picture is gone. So they used to have a very good picture about how they trained it. So how they trained it? Geez, I don't like this new revision they have. Let's see. Do they have a different version? They should have a picture in their earlier version on archive. Let's see. They have a picture about their architecture. I really like that picture. Oh, maybe in the appendix? No, the picture is gone. Okay, I'm deeply sorry. The picture is gone. Okay, all right, the picture is gone. So behind the scene, they use the attention mechanism, okay, and they compute sentence to they compute the self-attention between tokens within the same sentence, and they use that attention to compute a weighted sum of all the tokens, and then add all the weighted sum together as the semantic representation of the sentence. And we just see, hey, it really makes sense, even when there's no word overlapping with each other. All right, any questions about sentence embedding? However, there is a better way to do sentence embedding, as we will see when we move on to the next topic, which is a BERT model, which is an implicit use of the attention mechanism to do sentence embedding. Let's see, next one. Next one, let's see about a BERT, okay? So BERT so the transformer architecture, basically this transformer architecture made by Google tells us, just like the paper says, attention is all you needed. So in this paper, they show that with this transformer architecture, they could do any NLP task much better than before. That's why they say attention is all you needed. Okay, so and then people realize something interesting is that also challenging and beneficial. That's what I mean by interesting, is that think about it. This attention is very hard to compute, okay? Because if you think about it, this attention is a high dimensional function. Because think about, let's say the input, okay? We have, let's say, a variable length of vectors, okay? And we'll compute the self-attention. The term self-attention tells us the complexity is quadratic, because for every word in a sentence, we need to compute its attention with another of any other words, right? So which means that if the sentence has, for example, 5 words, how many attentions can we compute? We need to compute what? At least 12 pairs of attentions, right? Because the first word, let me use the how are you example again. So for example, for the word how, we need to compute the attention between how and the rest is 3 words. So that's how many? That's 3 attentions, right? And then for R, you need to compute the attention between R and these 2 words. So that's 2 words, okay? And for these 2 words, you need to compute 1 attention, okay? So for this word alone, you need to compute this many attentions, okay? And this increases quadratically, okay? So therefore, if you train this model, and it's further complicated is that here. So we're computed, so the attention function is between the embedding or the hidden state of 2 words. So the hidden state is usually high dimensional, or if you directly compute the embedding, if you directly compute the attention on top of embeddings of words, that's also high dimensional. Okay, so you're talking about building a high dimensional function, which has high dimensional function, and this function is quadratic. So which means that the attention neural network is very complex to train. So this became, initially this becomes a limitation of, as the first thought, you would say, hey, this is a limitation of the transformer architecture, because in order to train this attention function, this attention neural network, I need a lot of training data and takes really long time to train because there's so many parameters, okay? And not to mention that here, you also want to go to multi-head. That makes things much more complex. Okay, but however, interestingly, it turns out that this attention matrix, it remembers many intrinsic knowledge of human language. So for example, we say, how old are you? when we say old, we know that this how old means that what is similar to what is your age. And then something interesting is that, which means that the attention we learn, okay, it contains the general knowledge of, for example, English. Therefore, if you want to use this attention mechanism to use this attention model for another task, all you need to do is do slight tuning on it. Okay, so this opens a new horizon in NLP, which is called pre-trained language model, PTM, or it's called a large language models. And the BERT is the first paper to show that the attention mechanism can exhibit this property, that the attention we learned we can learn the general knowledge of a language through the attention mechanism, and therefore for any other tasks, you probably don't have to retrain this attention mechanism, start from scratch. This means that a language previously in machine learning, usually you train one model for one task, and this model cannot be used for another task. So for example, let's say you train one model to recognize whether in this picture, in an X-ray picture, the bone is fractured, okay? You cannot use this model to apply it for another task. For example, let's say in the image, you want to tell whether the blood vessel is clogged in another CT image. For example, you cannot do that. But language is a cool thing, is that, for example, when we speak English, regardless of what task you are doing, whether you are doing, for example, summarization task, or you are doing a inference task, the intrinsic nature of English does not change, okay? So for example, one sentence, let's say I give you a verbal sentence, say, oh, I'm sick today. It's because I eat this, because I get caught of cold, blah, blah, blah. Therefore, I went to class. Therefore, I teach my class online. So this is the paragraph, right? On this paragraph, you can do many tasks. You could do summarization. You can say, today I'm sick, so I'm teaching the class online. Okay, this is summarization. Or you can ask a question, say, what was the reason that I'm teaching the class online? Okay, from this passage, you can say, oh, it's because I am sick. You generate that answer because I am sick. So these two tasks are different, right? The summarization and the question answering, they're two different tasks. However, the intrinsic nature of the English language is there, is the same, right? Because the common sense is if you're sick, your behavior will change. So, for example, if you're sick, you will not teach the class in person, but online, okay? And the knowledge for between English words or the English sentences, they remain the same. For example, because I say, I am sick, you understand what I mean by I am sick, or I'm not feeling well, or I am ill. Those knowledge is the same, regardless of whether you're doing summarization or the question answering, okay? So that's the beauty of BERT. All right, so let's move on to the slides. So the BERT is based on a hypothesis that the attention, okay, which is the attention between sentence encodings contain essential nature of a knowledge. For example, we know that the bank and the money are always strongly related, okay? And therefore, the attention learned for one task just need to be tuned slightly to do another task, okay? And I just give you one example, right? Where you have summarization and question answering, okay? So those knowledge we can transfer them. So therefore, BERT's idea is that it will train attention on a task using a large corpus or a large corpora, and then we fine-tune the attentions using the data for another task. So for example, I could train the neural network to do summarization, okay? So obviously this network can only excel in summarization, it cannot do question answering. But we assume that the knowledge about the sick and the teacher the class online remains the same. So later I could just fine-tune this model a little bit. I feed in a little different training data, okay? The training data would be the passage and the question and the expected answer. Then after a few rounds of training, this network can do question answering very well. You can ask it a lot of questions, like for example, why I'm teaching the class online today, why Facebook's stock drops today, all those kind of things, okay? So this is a very cool thing, okay? And so this model trained on one task to be used for another task, we call it a pre-trained model, and such pre-trained model can be ported to any other different application scenario. And of course, you still have to train the model, but that train we call it fine tuning instead of training, because the training means you start from scratch when the neural network has no knowledge about a language. Okay, that is training from scratch. That is called training, or specifically in this context, we call it pre-training. So therefore, there are two kinds of training stages. One is called pre-training, usually is starting from scratch on a large number of training data. And the second thing we call it fine-tuning, which is training on a small amounts of data. Okay, so this is the idea of BERT. Why it's beneficial? Because it saves computational time, first of all, because a pre-training could take, for example, days to do, while the fine-tuning probably takes only hours to do. Second of all is that the pre-training could be done on various tasks to exhibit different knowledge of a language. For example, you could do pre-training using a mixture of question answering and the summarization, okay, to force the neural network to learn different aspects of the English language. So usually you can get something better than training using only one task, okay? For example, you can ask the network to do summarization, to do question answering, to do fill the blank, right? To do the close form, all that kind of things. All right, so let's look at the BERT architecture, and let's talk about how BERT what kind of task does BERT use to really train this model. So basically, a BERT is based on the transformer architecture. Okay, so it has many layers of transformer encoders. Okay, so remember when we were just talking about the transformer architecture, the original author has an NX. So basically, they have this kind of which they call sublayers stacked up multiple times. Okay, so I think the transformer paper they also used the 6 such stacks. A stack of height 6, while in BERT, the base BERT model actually has 12 such layers. Okay. All right, and BERT does something really interesting, is that it does not say it introduces some special tokens. Okay, so what it does is it has a special token here called CLS. Okay, CLS stands for classification, and we will see why this can be useful later. And then you have the sentence, okay? Then you have the sentence, okay? And the end of the sentence, you use this special token SEP, standing for separation or separator, to denote it. And BERT, because some tasks, we have two kinds of text. For example, in the question answering, right? You first have the passage, and you have the question. So you want to separate the question and the passage. So therefore, what you do is, you could use this separate. At the end of every sentence, you put the SEP token, special token. So for example, this can be your passage, like I ate something really bad today, so therefore I'm teaching my class online, okay? And then this part could be the question. For example, say, what is the reason I'm teaching the class online today? Okay, you can add as many SEP segments as you want, okay? You can do as many of them as you want. For example, let's say you have a weird task, is you have a passage, and you ask a question in English, and you want to answer in French, okay, you just add this separate multiple times, okay? All right, and BERT is designed such that they expect the entire sentence embedding, the entire input sequence, not only this one, okay, but the entire input sequence, their meaning will be aggregated onto the output of this special token. So how does BERT do that? BERT will do it by through training, okay? Which means that this special token will have an output, okay? And it just trains the task on the output of this special token and ignore the output of all other tokens. So therefore, hypothetically, through training, this CLS token will contain the meaning of the entire input sequence, okay? And you can imagine the meaning of the entire sequence will change depending on the whatever sentence you put here. For example, let's say the original passage is still here, okay? Is that I ate something bad, so I'm teaching the class online. However, depending on what the question you ask, the embedding aggregated onto the CLS token will be different. So one question could be, why are you sick? Okay, then in that case, the embedding of this CLS token will contain the reason that why I'm sick. But if your question is, why are you teaching it online? then the CLS token will contain the reason. So hypothetically, it will map directly to that because I'm sick. Okay. So that is the BERT model. Okay. So the BERT model, for every token, we will generate a self-attention. Okay. And we will assume that for each attention on every token, okay, the multi-head attention will have a dimension h, and we could have many, many heads. So if you read those papers, they are called A. So quite often you will see people describe the size of their BERT model. They will use like this. For example, L is 12, A is also 12, have 12 heads, 12 layers, and for the hidden state is 765. So this is actually the configuration of the base BERT model. Do you see something interesting? One thing is missing. We talked about the hidden state, right? And we talk about the sentence. But where's the generation part? Because if we talk about a transformer, we also have the decoder. Where's the decoder part? Okay. Because BERT only uses the transformer's encoder part. It does not use the decoder part. That's the reason. Okay. It only uses the encoder part, not the decoder part. All right. So here, let's see how it works. Here is a very good visualization made by Hugging Face. But here it shows a model which is they call distilled BERT, which is smaller than BERT. It's not the original BERT, but the architecture is pretty much the same, okay? Except the training and the parameters are different from BERT. So what it does is here, first of all, you have the input sequence, okay? So this example, this picture shows a very simple example, which is that what we want to predict what's the polarity or what's the sentiment of the sentence, whether it's positive or negative, okay? So therefore, the first thing we do is we tokenize the sentence. BERT uses a tokenization we're talking a bit. It's called a word piece tokenization. So, for example, this sentence is a visually stunning rumination on love. Okay, that's the original sentence. Word piece tokenization wants to break down suffixes or prefixes of words. So therefore, because nization is happened quite often in English, right? It means transforming something to something. Therefore, the word piece tokenizer will separate this word into two parts. And the word piece tokenizer will use a special token, 2 hash pounds, to know that this is not a single word. This is in this case, it will be a prefix or part of a word connected with another word. All right, so we do tokenization and we add the special token CLS and SEP. This task is a sentiment analysis task, so which means you have one single sentence as input or one single paragraph as input to get a number. Okay, so therefore we only need one SEP. We do not have 2 segments. We only have 1 segment. That's all we have. So this is your raw input. Okay. And then we will map them to integers. Earlier we talked about when we're talking about transformer, right? So you map them into integers, and you will see that the CLS token has a special ID in the embedding matrix, which is 101, while the SEP has a special token, which is 102. Okay, and these are the IDs for the other tokens. All right, and then what we do, we'll pass these integers to the embedding layer, right? We'll talk about embedding layer. The embedding layer is basically a lookup table, right? So then each of these integers will become a vector, right? And those embedding we talk about, we could train them using, for example, Mokolov's task, right? To train the word embedding. So then we use this ID to look up for the word embeddings, and that becomes the input of this BERT model. Let me show you the original paper. You know what? It's easier to use Google to do it. This universal sentence embedding. Where's BERT? Fine. It's easier to use Google to do it. So this is how it does. Okay. This is the input. Here's another example. Okay. So the input is my dog is cute. He likes playing. Okay, so you can see this is the example where we have two input sequences. We want to separately encode them, but you always begin with a special token CLS and use the special token SEP to mark the end of a segment of text which you try to process. Okay, and then you first find the token embedding for each of them. Okay, all right. So you can see all of them. You have the embeddings. While the special token, this one probably have embedding, this one probably have an initial embedding, okay? And then you need to have three things. The BERT input have three things, okay? Other than this tokens embedding, okay? It also has something called a positional embedding, which we just talked about. Basically, it's a sign function based on the position, okay? Because then, okay? And then you have another thing which is called segment embedding. Segment embedding is very simple, actually. You just use integers to represent which segment this sentence is. So here we have two segments. The first segment is my dog is cute, while the second segment is he likes playing. So therefore, we can use 1, for example, for the first segment, while 2 for the second segment, okay? While 0 for special tokens. So therefore, the embedding will do element-wise addition. So this one will add with the segment embedding, added with the positional encoding. Note that these two, they are scalars, while this one is a vector. So basically, you add a scalar onto every element of this vector. Okay. So that's BERT's input representation. Okay. All right. I want to show you a picture. I just recall a very good picture in Google's BERT. Let's see whether we can find it. BERT TensorFlow. They should have a very good tutorial here, which you visualize, because I mainly want to show the visualization. Oh gosh, it's not here. They change it all the time, actually. So it sucks. All right, so they don't have it. Oops, no. I don't want to show you my email. Let's see, BERT, TensorFlow tutorial. Do they have another tutorial? Maybe this one. Let's see. How do I get rid of this? Fine-tuning a BERT model. We just talked about. We just seen this. Oh, here, yeah, that's the picture. That's what I'm talking about. Okay. So you can see this we have seen, right? It represents the token ID. Okay. So the first thing is you want to map your input sequence into a bunch of integers. That's what you have. And then we have the mask model, the input mask. Okay. So this is input mask. Basically says this first sentence ends here. The rest of them are not. So this is a mask, which we will use being used for the attention. Okay. And second thing is the input type. Okay. So this is what says here in the paper. The segment embedding. Okay. Basically, we use one integer to represent which segment it is, and you can see it is here. So that's a segment. So the part left. So the 0 means this one means the first segment, which is the first sentence. This is the second segment, and the rest of them are just nothing. Okay. They use a binary matrix to represent different segments of the input sequence. All right. So if you use, for example, if you use a TensorFlow to implement BERT, you need this three parts: the input ID, the token ID being inputted, the mask, and the segment encoding. Okay. Any questions? All right. So let's go back here. All right. So how do you train BERT? Okay, we talk about that you want to train. So here we talk about one way to train BERT using a task, which is sentiment analysis. But let me finish. Sorry, let me finish. How does the BERT forces the meaning of the entire input sequence to be aggregated onto this special token CLS? So we will compute the self-attention between every token in the input sequence. Okay, we compute that, and then we could use the weighted sum. For every token, we can compute its contextual embedding, right? So for example, you want to compute the contextual embedding for these tokens, what do? We have the attention from this token to every other token in the input sequence, right? And then we do weighted sum of the embedding of the static embedding of all other tokens, okay? And the weights are the attentions. So which means that for each token, we could compute its contextual embedding. Okay, similarly for CLS. And you can see why CLS is special. Because CLS is not an English word, it's a special token. So therefore, the embedding on the CLS token is basically the weighted sum of all the other tokens, okay? And the weight is determined by the CLS to every token, the other token, which means that because CLS is not a real English word, the attention between CLS and the other token in this input sequence is basically, you can treat as the importance of every token, the other token in the sequence, right? So for example, we can imagine the attention between CLS and A is probably pretty low because A happens so frequently in English and it does not probably carry much semantic meaning. Of course, in some rare cases, probably carry. For example, with the and A, they're different, okay? But in this sentence, we can know that probably the attention between CLS and the word visual, stunning, rumination, and love is very high, okay? So when you do the weighted sum of these word embeddings, basically the output of CLS gives you a weighted sum of all the tokens, of the embeddings of all the tokens in this sentence. And therefore, this ALS token becomes a representation, a semantic representation of the entire input sequence, okay? But you may say, how do I train this attention from CLS to all the other tokens? And that has to be meaningful, right? Because we want, for example, the attention from CLS to A to be low, while CLS to visual probably high, right? And probably want the attention from CLS to rumination and love to be further higher than visually, right? Because the focus is on this part. All right, so how do we do it? We give you the task, okay? So from the CLS tokens output, we usually feed on another neural network, another machine learning model. It could be done through neural network or could not be done through in other approaches. So here in this example, the distilled BERT by Hugging Face, they actually do a regular machine learning model, which is not a neural network based, which is logistic regression. So they train a logistic regression model, okay, and then they want the logistic regression model to output two things. What's the likelihood that this sentence is sentimentally negative or positive? Okay, so it will predict a number. And we talk about this is basically softmax the result. And we will take the one that is largest because the probability for one is larger. So we say the final prediction is 1. So you can imagine, how do I train this model? If a sentence is positive, okay, I'll just let the output vector to be 0, 1. If the sentence is negative, I'll just let the output to be 1, 0. And if the sentence is neutral, I'll just let the expected target to be 0.5 and 0.5. And if, of course, initially the attention between CLS token and all the other tokens is a random number, so the network will make a wrong prediction, right? So therefore, I could do backpropagation. Okay, the backpropagation will not only update this model here, the second model here, but also update the contextual embedding on a special CLS token, and consequently, the attention between CLS and all the other tokens. You see, that's how it works. And through lots of training, gradually, not only this model will be able to work correctly, but also this model will learn the correct attention between CLS and all the other words. And note that the attention between CLS and all the other words is contextual dependent. Okay, it also because we have a softmax stage. So it also depends on the attention from CLS to all other words, and all other words, they are correlated attention. Any questions? One thing is that, remember when we were talking about CNN, we said the weights are shared, right? The weights are shared among neurons because as long as the weight is about the same filter, so they're shared. Similarly for attention. Okay, attention layer is actually a special neural network. Basically, you given one vector given two vectors as input, it gives you another vector as output. So when we computed the attention for the embedding of all the tokens here, or for the hidden state, each corresponding to one token here, they share the same attention network. So when you are updating this contextual embedding for the special token here, you update the same attention network between COS and all the other tokens. And if your task happens to be where you need to involve the tokens from other tokens other than COS, then those correlated attentions also gets updated. However, in this case, we only update attention through the contextual embedding on the COS token, not the other tokens. So that's what we mean by the shared part. The shared part is on the attention. Any questions? All right. So you can see, if I ask you to implement a BERT from scratch, it's not hard, right? If you don't use transformer, it's not hard, right? Because all you need is the embedding of every token, and you have another special network which takes two tokens embedding as input, gives you one value as output, which is the attention between these two tokens. Okay. All right. So let's continue. So how do we train it? So here we talk about a way to train it. We use the sentiment analysis task. We will predict the sentiment of the sentence. So you can have the ground truth, and this ground truth will create a gradient to train this attention network. So BERT actually used the two super simple tasks to train it, actually. The first task is called a mask language model, which is actually, we talked about it last time, right? Which is called a closed task. Closed task, basically, I have a sentence. Okay, I knock out one word, and I ask the neural network to predict what is that word. So this is called a mask language model. So you will see MLM quite oftenly. And another task is called a next sentence prediction. It just gives you two sentences and wants the network to predict whether the second sentence is actually the next sentence of the previous sentence in a real corpora. And you can imagine this can be done really easy, right? For example, well, I want to find for example, let's say you can use this paper as a training data. Okay, you take, so for example, you take a bunch of sentences. Well, this is not a good idea. Yeah, so this one, for example, you just take, this is the first sentence, this is the second sentence, right? So you input these two sentences as input to the model, and you want to predict one. And then you can do negative sampling. You let this be the first sentence, okay? And let this be the second segment of your training data, and you want to be 0 because this highlighted second sentence is not the next sentence of the previous sentence. Then you can, basically, you force the network to learn the causality or the, I'll say, correlation or dependency between two sentences, or discourse between two sentences. So these are the two tasks that BERT used to train. And so in the next sentence prediction, we can imagine that you will only use the output from CLS token, and the sentence you assembled will have two SEP segments, right? So this is the first sentence, this is the second sentence, and you want to predict using the output on the CLS token whether this sentence is the next sentence after this sentence in a true corpus. While when you do the mask language model, you do not need that. You only need the one segment part. Okay, and what you do is your input will become like this. So let me use a slide to explain. Your input will look like this. So for example, let's say I want to knock out the word stunning. Okay, so therefore my input will be CLS A visual masked. Okay, and the mask token has a special ID. Okay, and then rumination on love. Okay, and then when I want to do the prediction, I use the output on this masked token to do a prediction. Okay, and I want the prediction to say the word should be stunning. If it's not stunning, okay, no problem. I can use backpropagation to update the attention. Does that make sense to you? So I think in the paper, there is actually a picture showing how to do it. There is a picture in the appendix showing how do you do different kind of things. Class label, sentence. Okay, they do not have the mask part actually. All right, let's see what it mentions it. Okay, yeah, yeah, here we go. BERT will insert a special token called a mask, okay, in the input sequence. And it wants the model to predict using the corresponding token to predict the knocked out word, okay? That's the idea of BERT's training. Only using these two symbol tasks. And you can see these two symbol tasks, they have no application in real life, right? Because very rarely do we want the computer to predict the missed word in a sentence, right? Or to predict whether two sentences are causally related, right? But however, like I said, the intuition is that the attention would include enough subtle knowledge of the language. So therefore, even if you train on these two tasks, you can use this attention model for many other tasks like summarization, question answering, all those kind of things. All right. So let's talk about a special case. How do we use BERT for sequence labeling task? This is a quite frequently happen task. Okay. So for example, actually there's a true use of it, which is you can see in Google already. For example, if you ask Google a question, Google usually give you a snippet answer, right? They will find a paragraph on a web page, and then they highlight the answer corresponding to the question you asked for. So for example, here ask Google a question, why BERT has 512 token limit? And Google does highlight the answer, okay? It says the limit derived from the positional embedding in the transformer architecture, for which the maximum length needs to be imposed, okay? So how do we use that to do it? In this case, we will not use the output of, we need to use the output of all tokens, and not only those on the CLS token, okay? So what you do is, I think I have a picture to show how to do it. Yes, good. Let's look at the picture on this web page, okay? So this is what they do, okay? This picture, this is a very good picture. So what they do is, they will let, first of all, this is your input, right? So let's say this is my passage, okay? And I have my question, so this is all my entire input. Okay, I go through transformers, so this is the BERT architecture. And then each token will have a special, each token will have its output vector, okay? So from this output vector, I will predict, I'll make a prediction using a neural network. So for example, in the question answering, one way to update that is I can predict the beginning of the answer and the end of this answer. So for example, here what I need to do is I need to predict the beginning of the answer is from this word derived, while the end of this answer is on the word architecture. Okay, so then what I do is I train two neural networks. One, given the contextual embedding of every token, I predict whether it is the beginning of the answer. Second, it predicts whether it's the end of the answer. So therefore, I expect that the maximum output in the example on the slide will correspond to the word derived, while if I want to predict the end of my answer, I want the maximum activation to correspond to the token architecture. Okay, so that's how I use it to do the question answering or machine reading comprehension. All right, let's go back. All right, so that's it. Let's do. So you can see I train two neural networks. Okay, one predicts the beginning of my answer, the other predicts the end of my answer. So for example, here the question is what? Let's see. Here the question, here, see, this is the question, okay? You have a reference text and you have a question. Okay, the question is, how many parameters does BERT large have? And here is the passage, okay? So you can see my input is, like I said, we pack the passage and the question all together into it. And then here is a segment of the the BERT architecture. So this is the beginning of the question, the passage, and the rest of it is the passage and the question. Okay, and it trains two neural network. Here the author used the block start and end to represent, and we want the start to have the maximum activation starting from the word 300 and the answer to end at the word million. Okay, and then therefore we just need to scan the maximum activation for the start and the maximum activation of end. Then we can generate the segment corresponds to the answer that the author wants to find. That's the idea of how to use BERT to do question answering or machine reading comprehension. And you can imagine this can be used to do NER, right? So all you need to do is to teach your neural network. So given the input, teach your neural network. This is the beginning. This is input. This is inside, and end. And you can teach the neural network to do the NER tagging. All right. Any questions? And I do want to show you how you can use it to do very crazy things. Remember in the class, allow me to stop sharing a little bit because I want to show you that if you are working on the NER project, we have 5 teams working on NER project. So let me show you. There's one paper there's one paper which uses BERT to do it. I want to find that paper because I provide the paper on the handout. Example. Where's my example? Hold on, let me go to the sign up sheet. Give me a sec. I really want to show this before we end today. Wiki NER. Here we go. The EMLP paper. Look, good. Here we go. This paper. You can see you can use BERT to do a lot of cool things. So for example, here, this author uses it to do NER, okay? So you can see it uses mask language model. So what it does is, you see it has a sentence, right? Say somebody lives in Los Angeles. So it randomly masks out some words, okay? And then it concatenates the original input, the regular, BERT input, with the named entities, and it wants to train the neural network to predict in this mask location, the word should be lives, and in this mask location, the word should be Los Angeles. And from here, it wants the network to know that one of the masked position is the word Los Angeles corresponds to Los Angeles. Okay, it wants the neural network to know that this masked position is not a named entity, but this masked location is a named entity. And that's how it uses to do named entity recognition. Okay, so when it uses this model to do named entity recognition, what it does is this. Okay, you can read this paper. What it does is it assumes every word, it will mask out only one word in the sentence. So for example, here the sentence, Beyonce lives in Los Angeles, it will mask out one token each time and put the mask into here. Okay, and it wants this model to predict whether it's make a prediction. If the prediction corresponds to the actual word, okay, then we know, hey, this is named entity because this part only deals with named entities. Otherwise, it's not a named entity. And you can see this model always begin the input of this the network begins with the CLS special token. However, we do not make use of the CLS token. Instead, we use those masked out positions. I'm running a little bit fast. Let's go into details about this approach, okay? And I'll show you several approaches using this BERT model, to use modified BERT model to do various NLP tasks next time. All right, let's put a pause here. Any questions? All right, I see the message from Mario. It looks Portuguese. Yeah, sorry, Google says it's Spanish, okay? All right, yeah, but Spanish and Portuguese pretty much the same. All right. Any other questions?